You're in a room with a red button, push it, and there's a 50% chance a machine ends your existence instantly. We run the experiment again and again. Statistically, you should be gone pretty fast, except in the worlds where you are. This is a thought experiment, not a guide. We'll explain what the latest science actually lets us test and what it absolutely doesn't. We'll move from this imagined scenario to what 2025 quantum technology can really measure, and then to why most scientists still see quantum immortality as speculation. So how close could that button get to being real? When probability becomes personal. Now imagine that the same red button isn't tied to a cartoon version of danger, but to a functioning quantum apparatus in a controlled lab. Not a paper exercise and not a dice-rolling classroom stunt, but a piece of working equipment capable of producing a clear, measurable result from genuine particle-level behavior. The stakes here aren't sketched in metaphor, they're embedded in processes playing out at nature's smallest scales. Each press could be decided by an event so brief and fine-grained that, until very recently, no device could catch it in real time with meaningful detail. The line between theory and direct measurement is narrowing quickly. In 2024-25, the newest generation of quantum computing systems isn't just about stacking more qubits for computational bulk. It's about vastly improving the ability to isolate, steer, and measure them. Engineers have driven gate speeds higher and slashed error rates. Recent 2025 reports from NIST SQMS and leading industry roadmaps show coherence and fabrication gains that let researchers monitor quantum dynamics at far finer timescales than before. Improvements in superconducting qubit fabrication and the stability of fragile quantum states extend how long these systems can maintain coherence, offering a sharper view of how qubits evolve and interact before decoherence sets in. That shift matters. Where experiments once produced only statistical averages, blurred pictures built from millions of trials, researchers can now probe quantum systems with unprecedented time resolution and see how probabilities change as the process unfolds. It's not about watching a wave collapse as if it were a visible spectacle, but about tracing the dynamics and decay of quantum states with enough fidelity to compare directly against the fine-grained predictions of theory. It's like moving from hearing a headline about a coin toss to following the internal movement of the coin in extreme slow motion, minus the coin, and with particles doing the unpredictable work. In the imagined button test, this capability could be configured so that a single qubit's measured state determines the big picture outcome. Press the button and the system couples that microscopic decision to a trigger. What happens next in principle would hinge on a result quantum mechanics treats as inherently unpredictable, no deeper facts within reach to tip the odds one way or the other. These technologies make it plausible to link quantum decisions to macroscopic triggers for carefully controlled lab demonstrations, though ethical and practical limits keep this firmly in the realm of thought experiments. Physicists like Max Tegmark and Robert Squires use scenarios such as quantum suicide to discuss interpretational questions, not as something to build and perform in reality. Because today's machines can sustain and observe qubits with greater stability, scientists can better chart how subtle environmental shifts alter their predicted behavior. Those measurements reveal the signature of quantum randomness, statistical patterns arising not from hidden variables we haven't found yet, but from the nature of the system itself. For the first time, query-by-query tracking of a quantum state's evolution is accurate enough to follow a single instance of a microscopic event and chart how its probabilities shift before settling on an outcome. That doesn't give physical proof of alternate timelines. It simply gives clarity about the kind of randomness that such interpretations take as their foundation. From here, the idea of probability becomes less abstract. Life events aren't normally tied directly to the flicker of a subatomic system, but we all live on paths containing split points we only notice in hindsight. The glass that didn't break, the step you took a moment earlier than collision. In a quantum description, every one of those moments could correspond to a branching of possibilities. Modern experimental techniques don't show us branches opening. What they do is expose the bedrock randomness that, over time, accumulates into differences at scales we can see and feel. It's possible to imagine a chain of such quantum-dependent events, each with odds stacked against the same outcome repeating. Within an interpretation that allows all outcomes to happen in separate branches, there's always one thread that makes it through every trial, improbable in any conventional calculation but internally seamless to the observer traveling that thread. You press the button, a quantum event decides the result, and in that narrative you remain. Any version of you in branches where the other result occurred has no more access to your continuing experience than you have to theirs. The fact that existing hardware brings microscopic quantum decisions close enough to be tied to mechanical outputs we can directly verify is a change in kind, not just in degree. In a demonstration, you could watch a display switch between two outcomes, its timing and frequency matching numbers dictated by quantum mechanics for that particular setup. In those moments, you're not proving many worlds or securing personal immortality. You're watching the kind of decision point that, in theory, defines the boundaries of your timeline. None of this constitutes evidence that anyone could survive an endless series of such trials, nor that parallel histories exist. But it does bring the underlying physics that make the thought experiment conceptually possible within experimental reach. The randomness governing subatomic systems can now be tied, under controlled and ethical lab conditions, to macroscopic events in ways we can monitor without relying purely on statistical averaging. So the next time you think about being the fortunate one whose side of the probability curve always seems to win, remember that the mechanics behind that feeling are no longer just textbook abstractions. They are processes we can measure with unprecedented precision, shaping outcomes in the tangible world even when every setup is identical. And that opens a door to the deeper question of why, when conditions are fixed, nature still produces variety at all, a question that becomes unavoidable the moment you leave the world of imagined buttons for the smaller, stranger world of particles. Randomness is the rule, not the exception. In the world we normally deal with, patterns feel dependable. If you take a basketball and shoot from the same spot with the same motion over and over, the ball's path and result will hardly vary. Gravity, air resistance, spin, all of these forces behave in stable ways at the human scale. Control the conditions closely enough and you get almost perfect repeatability. That's classical cause and effect, reliable rules producing reliable outcomes. It's the basis for building bridges, flying planes, manufacturing electronics, and baking bread the same way twice. Now take that same mindset and shrink it far below what the eye can see. Replace the basketball with a single particle, say an electron fired toward a target. You prepare it identically each time, same position, same energy, same environment. Classical expectation would predict it striking the exact same spot in each trial, but that isn't what actually happens. Fire after fire, the electron lands in different locations, apparently without pattern. It's not sloppiness in the setup or a flaw in your measuring instruments. In the quantum world, identical preparations can lead to different outcomes every single time. This unpredictability is not an accident, it's how the physics actually works. This is quantum randomness. It's different from the surface-level randomness in a dice throw where unknown microscopic details, air currents, tiny shifts in angle decide the outcome but in principle could be measured and predicted. Quantum randomness leaves no such hidden trail. Even with perfect knowledge of everything measurable, you can only calculate the probabilities of the possible results. There is no deeper layer of information that would let you choose the winner ahead of time. To describe this, physicists use the idea of a probability wave. Before you measure it, a particle isn't fixed in one outcome or property, it's described by a spread of possible states, each with a defined likelihood. The shape of that spread is determined precisely by the equations of quantum theory, and it evolves predictably over time. But that predictability applies to the probability distribution, not to the specific result you'll get from any single measurement. Once you measure, the range of possibilities reduces to one actual outcome, and the others are excluded from the reality you continue to observe. This is a strange shift in thinking. Macroscopic objects made of vast numbers of particles moving collectively hide these fluctuations. A basketball's molecules average together into a path that looks fixed and predictable, but isolate the behavior of just one quantum object, and the underlying unpredictability steps out from behind the curtain. At this level, the universe behaves like a constant lottery, with new draws occurring everywhere and all the time, even in systems as small as a single atom or photon. The same probabilistic logic governs far more than just a particle's position. Whether a photon reflects or passes through, whether a radioactive nucleus decays now or later, whether a biological molecule changes its structure in one way or another, all of these are events set by probability curves, not rigid scripts. Over time, chains of these quantum events scale upward into the world you experience, influencing outcomes from the microscopic to the very human. Quantum mechanics treats these probabilities as reality's most complete description. Repeat an experiment under identical preparation, and while individual events will vary, the overall statistical pattern will match the theory's predictions exactly. This consistency is why we can design lasers, microprocessors, and medical imaging devices to work with remarkable precision. But the individual quantum events inside remain genuinely random. The fact we can rely on large number averages doesn't change that. Accepting that this unpredictability is built into the fabric of nature opens up thought experiments about what happens if you follow the logic to its extremes. In some interpretations, notably the many worlds view, every possible outcome of a quantum event occurs, each in its own branch of reality. In one branch the electron hits the detector, in another it misses. Scaled up, in one branch you make it through a dangerous event, in another you don't. The randomness becomes the mechanism that produces a branching structure of possibilities. In your own experience you get only one chain of events. But if other branches are equally real though inaccessible, then for even the most unlikely survival there is at least one version of reality where that survival plays out. It's the kernel of the so-called quantum immortality idea. Yet experts such as Max Tegmark have argued that in realistic causes of death, consciousness fades gradually, which complicates the naive thought experiment picture. And philosophers and physicists have raised deeper critiques. In particular, the probability and measure problems that challenge whether subjective survival makes sense in an infinite branching universe. In other words, the leap from quantum randomness to personal immortality is not a physics result. It's an interpretation-dependent philosophical inference with serious points of dispute. The everyday sense of causality, drop a glass and it shatters, emerges from billions of quantum-level events steering toward overwhelmingly probable macroscopic outcomes. In most drops, the atoms making up the glass follow the statistical pathways that produce breakage. On rare occasions, if you could replay the drop countless times, micro-level variations might alter surface stresses just enough to keep the glass intact. In the many worlds framing, both futures exist, each in its own branch. Most branches contain the broken glass, a few don't. That same branching logic is what gets applied, hypothetically, to life and death scenarios in quantum immortality arguments. The essential point remains: at the smallest scales of nature, randomness is not a sign of incomplete knowledge. It is, within our best physical theories, an unshakable rule. And because that rule operates as the statistical engine for all higher-level events, the range of possible outcomes across the whole universe is much wider than classical thinking suggests. Once you see the world in those terms, it becomes natural to ask how such probability landscapes look before a single outcome locks into place, and what it means to talk about an event existing as a spread of possibilities rather than a concrete fact. That's where the picture gets both clearer and stranger when you compare it to everyday experiences, and where the abstract concept of the probability wave starts to feel a little more familiar. Probability waves, Wi-Fi, and bad GPS directions. Think of what happens when your phone's Wi-Fi icon flickers between strong and weak. In that drifting state before it locks onto one signal strength, you have something loosely comparable to a quantum system before measurement. It's a distribution of possibilities, not a single value. Measurement, whether it's your device checking the signal or a detector checking a particle, forces one definite outcome. Unlike Wi-Fi, quantum probabilities are not just epistemic. Quantum theory treats them as intrinsic to how the system behaves. In quantum mechanics, a particle doesn't occupy a single fixed state in the way everyday experience suggests. It might be far more likely to turn up in one location than another, but until a measurement is made, those possibilities all coexist as part of a mathematical wave that evolves according to precise rules. Measurement ends that spread, delivering one clear result in place of many potential ones. The same idea appears in a much cruder form in how an algorithm predicts what you might watch on your social feed. Before you scroll, the platform holds a probabilistic profile of you, a catalog of possibilities weighted by how likely you are to click. As soon as you see a post and either watch or skip it, that cloud of options collapses to a single data point. The analogy works up to a point, but unlike quantum systems, these predictions rest on hidden, knowable causes: your past behavior, content popularity, server timing, that could, in principle, be fully mapped. Quantum physics lacks any comparable hidden ledger to consult. Its unpredictability appears to be built in. A less abstract parallel might be the moment you open a map app in an unfamiliar city. At first, your GPS dot jumps around, sometimes placing you inside a cafe, sometimes in the middle of the street. Until enough satellite signals arrive, the location is effectively a set of plausible positions, shifting and overlapping. When the system finally locks in, the uncertainty disappears with a single decision about where you are. In a quantum setup, the lock-in comes from an interaction, light scattering off an atom, a detector registering a particle, that fixes one outcome from the spread allowed by its wave. It's tempting to think of the blur in these examples as a defect, poor reception, imprecise tracking, but in quantum theory, the blur is not a symptom of bad measurement. It's what the object is prior to being measured, a structure that encodes every possible result of an observation and the probability of each one. The strength of this framework lies in how consistently its predictions match experiment. When particles are left unmeasured, their collective behavior follows the probabilities in their wave exactly. Once they're measured by any interaction large enough to extract a definite value, they behave as if every other possibility has been set aside. This change doesn't require human observers or mental will. It only needs a physical link between the system and its environment that can't be reversed. That's the opening where discussions about many outcomes existing in parallel begin. Mathematically, the wave before measurement is a complete description of every allowed result. Measurement narrows it to one outcome in your account of events, but nothing in the equations demands that the other results be erased from all of reality. For some, that means they remain real in separate branches, inaccessible but still unfolding. You can return to the Wi-Fi picture here. The full set of possible bars exists in the wave before you connect. You only experience one, but that doesn't automatically mean the rest have been annihilated. In everyday technology, we don't imagine the discarded signal strengths carrying on somewhere else. They simply didn't happen. In quantum theory, whether unobserved outcomes persist is one of the deepest interpretational arguments. Seen this way, the probability wave becomes less like a blurry photograph waiting for focus and more like an ordered list of all futures the system can take. Collapse is the point at which your path through that list is fixed, even if other paths remain meaningful in some wider structure. In interpretations like many worlds, collapse is not destruction but branching. Your timeline now follows one track while others carry on without you. This also reframes uncertainty. In most situations you meet day to day, uncertainty reflects missing information, data you could in principle gather to settle the question. In quantum mechanics, uncertainty is part of the object's definition until an interaction forces a decision. Better instruments won't reveal a hidden true state in advance. The most complete view you can have is the evolving wave of possibilities and the probabilities that go with it. Which brings us back to that wayward GPS dot. Its jumpiness before settling is caused by incomplete and noisy data, not by the intrinsic nature of your position. But it makes a useful stand-in for understanding that something, whether a signal, a particle, or a wave function, can be in a state defined by a set of possible outcomes rather than a single one. In the quantum case, those possibilities are not simply placeholders for the result you will discover later. They are an active, physical description of the system until the instant one probability becomes your single observed outcome. The rest is a question of what you think happens to the other options. That last point is where the practical, predictive side of quantum theory parts company from the interpretive side. You can work with the equations to design electronics, chemical reactions, or even experimental tests without deciding whether the unchosen possibilities persist. But once you start asking what really exists before and after a measurement, the conversation turns from calculation to the nature of reality itself. And that is exactly where physicists begin to split into very different camps. Two camps fighting over reality's plot. In professional physics, this disagreement is often framed as a split between two broad attitudes. On one side are the pragmatists, sometimes referred to as the shut up and calculate camp. They treat quantum mechanics as a perfectly honed set of rules for predicting experimental outcomes, without demanding that those rules reveal an underlying picture of reality. On the other are the interpreters, including many worlds proponents such as David Deutsch, Sean Carroll, Max Tegmark, and others, who insist that what the equations seem to say about the structure of reality deserves to be taken seriously, and if possible, explained. The divergence isn't over the math or the data, it's over the weight each side assigns to the question of what's really out there. Pragmatists see the theory as a kind of universal grammar. Master the syntax and you can write consistent predictions every time. Map out the wave function, evolve it with the Schrödinger equation, apply the correct operators, extract the probabilities. If those numbers match observations, and they do with remarkable precision, there's no pressing need to decorate the output with imagery about what happens in hidden layers beneath measurement. To them, the wave function is a calculation tool, no more real than the number 7 is to arithmetic. Interpreters argue that the wave function describes something physical, not just an abstract ledger of possibilities. When the math says a particle's probability distribution includes multiple well-defined peaks, perhaps those peaks correspond to actual outcomes that all occur, each in parallel. In the many worlds view, the branching isn't metaphor, it is the actual evolution of the universal wave function. Measurement doesn't erase possibilities, it locates you in one of them, while the others continue beyond your reach. Every quantum event creates more branches, and all of them are equally real within this framework. These opposing stances persist because so far no experiment has been able to tell them apart. The predictions of many worlds and other interpretations are, with current technology, empirically indistinguishable. That unfalsifiability means the disagreement is as much philosophical as it is scientific. For many working physicists, this is reason enough to leave the question alone. For others, it's precisely why the question remains pressing. Much of the philosophical back and forth boils down to this. Pragmatists focus on predictive power and reliability, arguing that physics isn't obliged to provide a metaphysical story. Interpreters see a missed opportunity in declining to confront what the equations appear to imply. One group finds satisfaction in stopping at the math works, the other sees that as only half an answer. The popularity of many worlds among some interpreters comes from its elegance. The equations operate without modification and no special collapse rule is needed. You get branching simply by following the math, solving the Schrödinger equation for the whole universe. From here, speculative ideas like quantum immortality emerge. If branching is real, then in every situation with a non-zero chance of survival, there exists at least one branch where you live on. Your subjective experience could, in principle, follow that unbroken survival thread indefinitely, however improbable it looks from an outside perspective. Pragmatists push back hard against that leap. Accepting many worlds as the literal truth is one thing, layering on a personal survival guarantee is quite another. The equations do not privilege one branch over another, nor is there evidence that consciousness chooses the survival path. From a single world standpoint, the outcome of a life-threatening event is whatever happens in the one reality we share, determined by chance but final in its consequences. Between these poles sit a range of intermediate positions. Some physicists hold that the wave function is real but does collapse under certain conditions, which trims away the extra branches without abandoning physicality. Others speculate about undiscovered rules that might reconcile the apparent randomness with a hidden order. Still others borrow elements from many worlds without accepting it wholesale. Regardless of stance, everyone uses the same formalism to do the actual work, designing experiments, operating quantum devices, and testing predictions. That shared toolbox is part of why the disagreement hasn't stalled progress. Quantum mechanics powers technologies from lasers to superconducting circuits to quantum computers, all of which rely on the math, not on winning the interpretation war. In the lab, calculations matter more than metaphysics. In thought experiments, however, interpretations like many worlds can radically change how you imagine your own trajectory through the universe. Personal perspective plays a big role here. If you adopt a single worldview, improbable survivals are just luck, and luck eventually fails. In the many worlds narrative, somewhere in the branching wave function is a continuous chain of versions of you that keep going, no matter how many close calls occur in other branches. The same equations support both views. The difference lies entirely in how you think about the outputs. The split runs deep enough to have persisted for decades, and the lack of decisive experimental leverage keeps it in place. A definitive test, one that could clearly distinguish a single persistent world from an ever-splitting wave function, would be a turning point. Until such a test exists, the debate stays open, with pragmatic restraint on one side and interpretive boldness on the other. If you assume the literal branching picture, then right now there are versions of events in which every allowed outcome is playing out. Among them is a narrow run where every hazard misses you purely by chance, and that run is the only one you would ever be aware of from the inside. Whether that strikes you as a comforting loophole or a hollow abstraction depends on which account you accept. And before weighing that reaction, it helps to understand exactly what the many worlds idea does and does not claim, especially compared to the popular images it often gets mixed up with. The quantum crossroads, one world or infinite branches. At this crossroads in quantum theory, the many worlds interpretation offers a radically simple answer. The universal wave function is not just a calculation tool, it is physically real, and branching is an unavoidable consequence of its smooth, unitary evolution without collapse. In this account, quantum mechanics never chooses a single outcome. Instead, every possible result allowed by the wave exists, each in its own branch, and all branches together make up reality. When most people hear many worlds, though they tend to imagine the tropes of science fiction, parallel Earths with wildly different histories, or neat timelines that can be crossed if you find the right machine, that picture misleads. In modern physics, many worlds describes an unbroken, continuous process occurring at the smallest scales. Every time a quantum event unfolds, any situation where the probability wave allows more than one result, the structure of reality incorporates all those results. There's no dramatic fracture, just steady, microscopic accumulation of differences as branches form. Quantum event can be as unremarkable as an electron taking one path instead of another in a microchip, or an atom releasing a photon now rather than a nanosecond later. Before any measurement, such alternatives coexist in the wave function. Afterward, in the many worlds view, each is real in its own branch. These branches are not separate universes floating side by side in space. They are distinct components of the single universal wave function, which evolves without discarding any terms. The branching is constant, happening in countless systems around you at every moment. In everyday terms, branching unfolds quietly, even when you seem perfectly still. The molecules in your body are constantly involved in quantum processes with multiple possible outcomes. Every one of these outcomes plays out in some branch. The sheer pace and number of these events make the branching structure unimaginably vast. Attempting to list even the splits of the last second would be hopeless. From your own perspective, though, you never sense this multiplication. You experience a single, continuous history, the sequence of events corresponding to just one path through the branching web. Suppose a quantum coin could land on heads or tails with equal probability. In this interpretation, both happen one in each branch. In the heads branch, a version of you saw heads. In the tails branch, a version saw tails. After the split, their futures diverge independently. Why don't these versions interact or exchange information? This is where decoherence enters. Decoherence is the process by which different outcomes, though part of the same overall wave function, rapidly lose the ability to interfere with each other because of their entanglement with countless environmental degrees of freedom. Once that entanglement happens, the branches are effectively sealed off. Each continues to evolve according to the same laws, but the correlations that tied them together fade beyond retrieval. Decoherence explains why the branching appears clean and why you feel locked into one branch. However, as research points out, it doesn't by itself solve the deeper measure and probability questions. Physicists like David Deutsch and David Wallace have developed decision-theoretic approaches to explain how the standard quantum probabilities might emerge within many worlds. Others, like Lev Vaidman, have critiqued these ideas or offered alternatives. The mechanisms are under active debate even among proponents. Understanding this split between mechanism and interpretation is easier if we separate the ideas. Branching means that all possible outcomes of a quantum process remain in the universal wave function. Decoherence explains why those outcomes stop interfering and act like separate worlds. Your perception of a single, unbranching reality is simply the subjective view from inside one decohered branch. This interpretation also reframes familiar cause and effect. Each moment in your life sits on the surface of a vast tree of branching possibilities. Walk through a doorway and photons scatter into your eyes in one particular way in your branch, but in another, slightly different scattering pattern in another branch.